All right. Good morning, everyone. Welcome back to Math 154. As always, this is week 11, lecture 2. Per usual, going to go over a few due dates before we get into where we left off. So 5.1, 5.2, 5.3, we've already discussed those due dates previously. 5.1 and 5.2 due on the 9th, 5.3 due on the 11th. And then 5.4 we will finish today. We will also start 6.1 today, but we won't finish it. So that's why you don't have a due date on the screen. We'll finish that next time. And I just wanted to point out that with 5.4, the section title is a little misleading because it does have statistics in the title. And you might be thinking, Mr. Beckner, at the beginning of the semester, you always said we wouldn't do anything with statistics. And I stand by that statement. That is still true. We are not going to be doing any statistics. So then why are we doing 5.4? Well, the topics that we're going to cover in 5.4 used to actually be in 5.3 before the text edition changed a year or two ago, something like that. So the stuff we're going to do in 5.4 isn't statistics. It's going to be centered around something that's conceptually statistics, but we won't actually do the statistics. It's this idea of linear regression, which is a great way of taking a bunch of real world data and making a model out of it. So what we're going to do is we're just going to take the data, put it in Excel, or I already have the data in Excel, and say, hey, Excel, do my job for me. And it boom, 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 does it for you instantly. Versus if we actually had to do this linear regression math on our own, it would probably take me 2 weeks to teach it to you. And every problem takes a very long amount of time to actually do. It's a very time consuming process. So again, we won't be doing any of that time consuming process. We're just going to learn how to, hey, this information's in Excel, highlight it, do some stuff, boom, there, that will get you your equations, that'll get you your graphs, that'll get you how good of a model it is. So that's what we're going to talk about in 5.4. So it's statistics related without actually doing the statistics. We also mentioned last time that we have Excel 5.1 lines and video quiz 2, which I believe is our 5th or 6th quiz in total, both due on the 11th. You will get video quiz 3 assigned next time, which is going to be covering chapter 5. And then after that, we're going to get video quiz 4, which will cover a combination of chapter 6 and 7, because we will not cover all of chapter 6 and all of chapter 7. In fact, we're just going to do 2 sections from chapter 6 and very briefly discuss a video from chapter 7. And then we go into chapter 8, and then we go into chapter 9. So chapter 6, 8, and 9 are going to be a lot shorter in terms of the breadth of material we cover versus everything else we've done, where it was 4 sections from chapter 1, 4 sections from chapter 2, from chapter 3, from chapter 4, from chapter 5. Might be a slightly misleading statement. Chapter 9, we do cover a very wide breadth of material. We just do it on a much lighter basis. But we'll save that for week 14 when we actually get there, week 13, week 14. So at the end of last class, I might have said that we were going to pick up in a guided activity from 5.3. I think I might have said that. I'm trying to bring my thoughts back a week to when we covered that. And if I did say that, I did not mean to mislead you, but we're not going to. We're going to go straight into 5.4. I was kind of partitioning times for the next several classes, and I realized we wouldn't have time for that, so we're not going to cover it, and that'll be fine. So we're going to go right into this concept of linear regression, and here we go.
To that guided activity from chapter 5, specifically, long dramatic pause so I can find it. All right, so I said that, big zoom, this says the following things go in 5.4. Okay, you could argue that they go in 5.4 because this is going to be Excel using something known as linear regression, something that we're not going to talk about at all, except for the fact that we let Excel do the job for us. But because we're not actually talking about the mechanics of it, we can still borrow these Excel charts. They were perfectly fine in 5.3 like they were in the original edition of this book. So we're not going to be doing any of the crazy statistics. We're just going to kind of talk about how it relates. So something that I have mentioned numerous times already, in the real world, quantities don't always vary in a perfect linear fashion, especially when we talk about financial dynamics, especially when we talk about anything having to do with people, pollutant concentration, as they kind of talk about, blah, 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 blah. So sometimes instead of saying we get an exact linear model, we just say it's a linear trend where the line can approximate some of these things, but it's not necessarily going to hit that nail on the head perfectly. So like here, if you look at 1985, this dot is perfectly on the line. This one's kind of far off. This one's kind of far off. And when I say kind of far off, that's subjective, of course. And then this one is exact again. Now, we went through a process where we actually made a line and we we are about to do that, never mind. So you might say, well, why not take a line and just anchor it from the first and the last points? That's actually a good method, and that's what we're going to do. The thing I thought we talked about, but that's because I've just done this so many times that sometimes I forget what I haven't done. All right. But just using a first and a last, that's not always a good approximation, especially when you want to go outside of these boundaries. Sometimes it may be a little better inside. Sometimes it may be a little worse inside. It just depends. So this right here, what you're looking at, this is what's known as a line of best fit. A line of best fit. So Excel uses this thing called linear regression. It's this mathematical process that it's the thing I mentioned probably last class that it would probably take me a month to teach it to you. It's extremely tedious. It is very time consuming. And we thank Excel for doing all of that work in the snap of a finger for us, because that's the beauty of computational mechanics. So this line is considering every single one of these points, and it's trying to, you could think about it as trying to minimize the average distance from the line to the point in a vertical sense. If that confuses you, don't overthink it. Just think that it's trying to make this line fit all of these points as best as possible in consideration of all of the points, not just the first and the last, which would be like an anchored method. So Excel somehow chooses this best fitting line, the line of best fit that I mentioned, and they say that we'll talk about it in chapter 8, although we actually won't. So Excel manages to come up with this equation, and I showed you how to get this equation last time. So if you don't remember how to put that in an Excel chart, then go back and watch last class's video. That's the beauty of these recordings. I don't have to always repeat myself. So we have our slope and our y-intercept. Now that y-intercept had an e, which meant it was times 10 to the 7th, which this is like a 4 with then 7 zeros after it, a very, very big number, or because it's negative, technically a very, very small number. So that's saying that the y-intercept is negative 40,000, which we're talking about millions of dollars. So remember, the y-intercept talks about back at 0, which since this is years, we're talking about year 0. And that makes no sense for several reasons. First of all, we're talking about Social Security outlays or expenses. So that means that at the year 0, we were spending negative $40 million on Social Security. Well, that's impossible because the least we can spend is, a penny or $0 more specifically. So how do we have spent negative $40 million? That doesn't make sense. Another way it doesn't make sense is, why would we even talk about Social Security in the year 0? America did not exist. Social Security definitely didn't exist until FDR's New Deal in the, don't quote me on this, 40s, roughly. Again, roughly. I'm not a history teacher, so please don't judge me there if I'm off by a decade. So it would not make sense for this model to even go further into the past than when this idea was started, because 1 year prior it was 0. The year prior to that it was 0. All those others it was year 0. So it's more like this model would be like, all right, 0, 0, 0, 0, 0, and then your New Deal starts, and all of a sudden your Social Security expenses pick up, and maybe they actually pick up in a model that looks more like this, which they did not do it that way. They used dots, so they're like 0, 0, 0, 0, 0, just for single years, and then all of a sudden the New Deal happens, and then we get our expenses and whatever that actually looks like if you looked at a longer span of time than from 1975 to the current year, or at least a few years in the past. All right, so that's our ultimate goal, is to kind of deal with that. But for now, what we're going to do is that anchored method I was kind of talking about. Instead of actually accounting for every single one of these points, all we're going to account for is the first one and the last one. We're going to make a line connecting them. We're going to find its slope. We're going to find its equation. And then ultimately, we're going to take that anchored model and we're going to compare it to the model you're looking at without the anchors, where all of them are being used. So that's what this says. Guided activity 1. The following table gives the amount of money spent on Social Security in this country in millions. So this is not 64,000 blah, blah, blah. This is 64,000 million, which would be really 64 billion. So this right here is not 944,000, it's 944,000 millions of dollars, which would really be 944 billion, and again, some change. Take the first and last data points, which they remind us are here. First, last, see 2020, we didn't have this data yet, that they only have up to 2017, so that's why it's blank, so we can't use 2020. 2017 is the last completed one, and we want to find this slope. All right, so I'm back to, I don't really think I'm going to be able to do this on another page, so you're just going to have to deal with me writing on this in my ugly handwriting version without that program helping me, as well as having to erase it quickly to move on. So our slope is y2 minus y1. That's the difference of the money values, then 944,878, and then millions, minus then that's 64658, all divided by the change in the x values, which is 2017 minus 1975. All right, and I am going to go maybe a little bit quicker today. So that top should be 880220, yes. And then the bottom, 2017 minus 1975. That's 42, right? Yes. And then I can't pull up my calculator right now, so you'll have to trust me that if you do this division, you're going to get, doing this manually, 20957.62. If you round it to 2 decimals, they say to 1 decimal though, so 20957.6. So that's 20,957.6 is our slope. So that's the number we can put in our equation if we were writing the equation here. So we'll hold on to that number, write that down because it's going to get erased. So write that down. Right, just like all your notes, you should be writing down. And then they say to interpret this as a rate. So that sentence, that cookie cutter sentence that we have done before. So we would say that Social Security outlays, that's the output, expenses. So outlays, expenses, same thing. Social Security expenses have been, well, the slope is positive, so I can be, instead of just saying changing, I can say has been increasing at a rate of, and then this is where we use the slope, 20,957.6, and that's in millions. So 20,095, I may have said that number wrong, but I've got it right here, 57.6, and then millions per year. Not per year since 2000. We never said that anywhere. It's just per year. We are considering the year 0 in this model, whether we should or not. Now, if you didn't want to write this in that goofy 20,000 millions, you could have said $20 billion instead, with all the other numbers in place, and that would have been okay. So again, that's our slope. Hold on to that. Don't delete it from your brain. Write it down, whatever you have to, because we're going to use it again. But I do have to clear my screen. All right, next they say, draw a line between the 2 points on the following graph. Now you might be thinking, 2 points? 2 points? I see lots of points. I see way more than 2 points here. They're talking about the 2 points that we used from the slope above. They're talking about the first and last. Again, I call this an anchored approach. We have the line of best fit, and then we have the anchored approach. This is not an official term. This is just what I call it because it's like we're using the first and last to anchor, to tether a rope together. So we don't care about what happens in the middle. We're just drawing a line between them. Now, I'm going to do this wrong at first. Here's what I see a lot of my students do, and we actually get to work together. They just make all these bunch of little line segments, just drawing straight lines between each of these. And I know these are a little curvy, but I'm doing the best I can. Imagine those were all teeny little line segments, and it's wrong. They did not say draw a bunch of line segments. They said to draw the line from the first to the last point. So we're just trying to connect the first and the last. I'm going to try using something to make this a little better, but it's still going to be difficult. All right, so that's there. And this one, oh, that was a pretty good guess. I think I got it on my first try. Look at that. I will never do better than that quickly. You just witness history. I used a folder to kind of anchor my dots, but I placed it perfectly on the first try. And again, if I didn't, I was going to have to move it blindly until I got it right. So there's our line. And of course, I had to goof up the arrow just a little. Let's make that look a little prettier. There's our line. Just connects the first and the last. This is the anchored approach. So that's it. That's the entirety of problem 2. We can see that there are bigger gaps here, 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 and even here, versus that previous example. This is just me showing a gap, how far off the estimator, which is the line, is from the actual data, which is the points. Whereas before the line, let me just try and draw something that's pretty close. Before the line looks something like, it was a little below on the ends. Oh, I'm gonna nerf this. I'm gonna do my best. It was something like this. This was about what the line looked like before. That was the previous page. So we can see the red line's a little higher. The blue line's a lot closer to a lot of the dots. It even went through a couple dots. I think I even nailed the specific years it goes through. I might be off by one. Doesn't matter. Again, that was just a quick attempt. So they're not the same picture, they're not the same slope, they're not the same intercept. They make different approximations. You might think that that blue line is always better because, oh man, look how bad this one is in this section. It's so much further off than at the beginning and the end, especially in comparison to the previous one. However, while it may be better in this region, if you go 5, 10, 20 years in the future, maybe the red one's better. We don't know, and I'm not saying that this is always better. I'm saying it's kind of a flip of a coin. It's going to vary from problem to problem. All right, compute the equation of the line by plugging in a point from before and the slope that we found before. So before we knew that the slope was 20,957.6, and that was in millions. And the point that I'm going to use is the first one. You can certainly use the 2017 and whatever value that was, but I'm going to use the 1975, 64,658. That's the point I'm going to use with that slope. So that's our x and our y. This is the x value. This is the y value. This is our m. So we just plug those numbers in. So the y value, 64658, is equal to the m, which is 20,957.6, times the x value, which was 19. That's a 75. I know it kind of looks like a 9. And then plus the b. Again, I just plugged those three numbers into those three variables. We don't know the y-intercept. That's the whole point of what we're doing here. Again, just trust me on this calculation and please try it out on your own as well. 20,957.6 times 1975 is going to be 413,64658 equals 413,912.60. Then we have our plus b. So that means we got to subtract that number on both sides. I'm just going to abbreviate it in the negative 413 dot 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 dot. It's a terrible looking one. 413 dot 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 minus 413 dot 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 dot. Just saving myself some space. And then if we subtract 64658 minus that 41391260. Hold on, I just typed it in my calculator. You get 413,266,02. 413,266,02. Okay, that's right. So that's our B, that's our y-intercept. That's like our starting value, right? Question mark? I did something wrong intentionally just to see if everybody's on their toes. I have this as a positive value. But if you take 64,000 minus that number is really 41 million, this is definitely going to be a negative. So I was trying to keep you on your toes there. So that's a negative B value, which quite often negative B values don't make sense, especially when talking about money for an expense or population size or something like that. All right, so now that we have the M and we have the B, we're going to plug them in to the, to the M and the B in the standard equation, but we're going to keep the y and the x. We're not going to plug in that point anymore because we want to see what this thing is forever and ever and ever. So it's y equals 20,957.6x and then minus 413,26602, which is 41,326,602. Now again, that is actually in millions, so that 41 million is really 41 billion. I'm sorry, if it's in millions, we're adding on a whole set of 3 zeros. So trillion, that's representing 41 trillion in a negative aspect, because everything is in millions of dollars. So this is the equation, but note that the y-intercept doesn't make sense. Just like the y-intercept didn't make sense for the thing that Excel gave us that we didn't show the process of finding, we just showed it on the screen. The y-intercept doesn't make sense because it's a massively negative number. So at year 0, there were negative $41 trillion in expenses? Absolutely not. That is a horrible prediction. The least it could have been would be 0. And again, it wouldn't even make sense to go further in time backwards past the 40s or 30s or 50s, whenever that New Deal started officially. So question 4, I'm going to have to erase this, unfortunately. So just kind of hold on to that equation. Hopefully you wrote it down. I'll read the question while you're finishing that. Where does your line look like it will hit the vertical axis on the graph? What year does this vertical axis correspond to? How does this relate to the value of B in your equation in number 3? So where does it look like the line will hit on the axis? It looks like it hits, well, exactly here, because this is the axis. However, it's not a true y-axis because it's not representing the year 0, it's representing the year 1975. Remember, a true y-axis is supposed to start at 0, which this does not do. However, many times in the real world, we draw up axes that are not a true y-axis because they don't start at 0. So where does it look like your line will hit the vertical axis? It looks like it hits maybe about, I don't know, 60,000, 75,000, something like that. It's about 3/4 of the way down. If I just undo circling that point. There we go. Apparently I'd done a lot more. You can see that it's maybe 3/4 of the way to 100,000. So I'd say that's about 75K, and again in millions, so that's really 75 billion. What year does this vertical axis correspond to? Again, while not a true y-axis, it represents the year 1975. I'm just skipping writing sentences. How does this relate to the value of B in your equation? Well, it doesn't. It's not B. It's not the y-intercept because the y-intercept is supposed to represent year 0, whereas this represents the year 1975. So what I'd like to do really quickly is show you what this line would actually look like. So if we have, and that's going to be a terrible way of doing it. So here is somewhere way over here is 1975 and somewhere about the year 2000. And this is about the points that we have right there. Then over here, this will be the year 0. And if you trace this line all the way back, then this point right here, that would be the negative 413.26602, which again doesn't make sense. This is where you should actually stop. You shouldn't look anywhere past that in terms of going into the past, because it doesn't make sense to talk about years before 1940-ish. It doesn't make sense to have answers that are negative in terms of Social Security expenses. Okay, so let's clear our screen. Again, I hope you wrote that equation down, because it's going to come up again. maybe not, at least we'll compare to it. Now fill in the years since column. So there was a column here that was blank above, and now what we're going to do is fill it in. And this column we want to be the years since 1975. This is going to go pretty quickly. It's pretty easy to do. In 1975, that's been 0 years since 1975. In 1980, that's been 5 years. 1985, it's been 10 years. 1990, it's been 15. 95, 20. 2000, 25. 2005 would be 30. 2010 would be 35. Then 2013 would be 40, right? No, wrong. See, a lot of people get stuck right there, and they go, oh, okay, I'm just adding 5 years over and over and over. What's happening? Pay attention. You get used to, oh, it's just going up 5, 5, 5, say 5, 5, 5, 5, 5, 5, 5, 5, 5. But no, this only went up 3 more, so that's 38. Then 2017, that's another 4, so that's 42. 2020 would be 45, and there's still no Social Security outlays there. So we can't use that as a true point. Now compute the equation of the line going through the point. Now instead of using the true years, we're using the years since. And I've addressed how this can make better models on a short-term scale. It would make much more sense to only look at years in the range of when Social Security even exists. Now, we're not starting at the beginning of Social Security in the 40s or 50s. We are starting a few years into it, but that's okay. I could choose to start in the year 1980. I could choose to start in the year 2000. That's not the big deal. The big deal is that I'm trimming this from looking at 2,000 years worth of data to only about 50 or 60 years worth of data. All right, so now what we're going to do is compute the equation of the line going through the points. So now these are the same y values. It's the same y values as before, but it's the x values that are new. Instead of using the actual years, we're using the years since. Now, we've already done this in the past. We saw that we got a same slope, so hopefully that's going to happen again. It's just the intercept ultimately ends up being different. Now, I do need to clear my screen so I can give myself just a little more space. But those years since should be pretty easy to fill back in if you need to. All right, that'll work. I like red. Okay, so our slope, m, is y2 minus y1, so that's the 9, 4, 4, 8, 7, 8 minus the 6, 4, 6, 5, 8, all over the x2 minus x1, which is 42 minus 0. And when you do your math here, the top subtraction is the same. The bottom, the numbers are different, but the subtraction is the same. So you end up getting the exact same slope value of 20957.6. It's the same. But when we plug in the slope in one of these points, the y-intercept will be different. Let's switch to blue for that. So for the y equals mx plus b, we'll plug in the y, the m, and the x in order to find the b. It doesn't matter which of these 2 points you use, pick whichever one you prefer. I have said that if I've got a 0 somewhere, I prefer that one, and it's going to make this go really smoothly. So I'm going to choose this point. So the y value is the 64 grand, the x value is the 0. So 6, 4, 6, 5, 8 equals the m value, which is 20,957.6 times 0 plus b. Anything times 0 is 0. So we get 64658 equals b, which is our y-intercept. So that says that the starting value is 64,658 at 0. But we're not saying year 0. We're talking about years since 1975. That's our 0 for this model. which makes complete sense because that is exactly what we have the number being. So ultimately, our equation is y equals 20957.6x plus 64658. This intercept makes much more sense because it's a positive value and it's in the range of values that we see. So for the 500th time I've probably said it, doing years since is a much better linear model than years. All right. How much further do we want to get in this? So it's the same slope, but a different y-intercept. Hold on to that equation. If you didn't write it down, you got about 5 seconds to write it down. Snap a picture real quickly, whatever you have to do, because it's going away. 3, 2, 1, it's gone. This. Too far. Now consider the trend line, the best fit line from the very beginning. I can't read that, unfortunately. In the graph below, how does this line differ from the one you drew? So now consider the trend line, which is right here. Now remember the one we drew, let me just really quickly put it up in black. The one we drew was anchoring the first and the last, and this is gonna not look as good because I'm not gonna take that time. That was the one we drew. So you could say that our line is a little above, or you could say the best fit line, which is the blue one, is lower. And that's about all you can really tell. Some people might be able to do that accurately enough to assess the slope, but that's really all I'm going to say. Then they say use both your lines. Sorry, use both your line, the equation that we just came up with, the thing that was just erased, the very last thing we wrote before erasing, and the best fit line to predict Social Security outlays in 2020. So we're going to use this line of best fit, and we're going to plug the year 2020 into that, maybe not plugging 2020 into it, but whatever represents the year 2020. Then we're going to use what we called, will that look good? Okay, yes, it will. The anchored, which was y equals, I wrote my numbers down, 20957.6x plus the 64658. So we're going to plug in whatever represents the year 2020 into the line of best fit, which Excel found the equation for us, and it always will, as well as the anchored one, which we found. See, the anchored method is very much an archaic version of the line of best fit. Again, we just don't consider all the middle points because, I mean, you saw how long it took just to do 2 points. Imagine trying to do that with all of them, especially the extra statistics stuff that's involved. It's horrible. All right, so for the best fit, BF for best fit. Now the year 2020, that represents, what year are we plugging in? 2020 in comparison to 1975 is going to be 45 years later. That's the number we're plugging into these two equations, not 2020, we're plugging in 45. So it's y equals for the line of best fit. And see, this equation is not the exact same because this equation, as the very original one, the original one had like a negative 7 million or 70 million here because they were considering all years. This is switched to years since. So that makes it more comparable. All right, so 20,559 times 45 minus 16,869. All right, so that's not going to be, I got to go off of this. This is where things just get a little weird, which is why I didn't want to do it earlier. 20,559 times 45 plus, I'm sorry, minus, excuse me, minus 16,869. And we get 908,286. Why does that look wrong? 2,559 times 45. 869. 869. Okay, that's fine. I have a handwritten error, that's all. That's what was throwing me off. Oh, shoot. This is why I don't like that. I always get confused. So that number is 908286. Then for the other one, for the anchored, it's y equals 20957.6 times the 45 plus 64658, which when we calculate that, 20957.6 times 45 plus 64658. And we get 1,007,750. And then the ultimate question is for number 10. That was off circled, isn't it? There we go. Do you think the actual spending will be more or less than the estimates from number 9? In other words, which one do you think is a better predictor? Which is better out of these two? So we're talking about the year 2020, and we want to know, is it the 900,000 or the million? And again, just tack on 6 extra zeros after those. So that's 908 trillion, or I'm sorry, billion versus 1 trillion. Well, look at this. Look at this year right here. If you trace that all the way over with a straight line, that number's already over 900,000 in the year since, which is 42, which would be 2017. Now look at these points. They're always going up. So I would say in the year 2020, I would anticipate that this dot is going to be somewhere higher. Now it may be a little higher, maybe a lot higher, but it's probably going to be at least jumping as much as they have in the past. Now, if you jump just that far, you're already in the 1 million range. So I would actually say it makes more sense for it to be the 107. And in fact, if you look at the table, this point right here was 944,878. This number is lower than that. And Social Security expenses have never gone down, so why would you think all of a sudden they're going to start going down? So I would say that this is the weaker answer, and that the other one, the million, billion, trillion, would be the better answer. So do you think the actual spending will be more or less than the estimates than 9? I would say more. All right. So that is that. The guided activity on the further pages down up to like 219, I really love that activity, but we just don't have time to do it, unfortunately. Let me clear my screen, go off to annotate. I'll at least show you and just really, really quickly talk about it. This activity is all about, there's this classic statement that half of all marriages end in divorce. And it's actually a pretty weak statement ultimately. That statement comes from the fact that in a given year, in the recent years, that is to say, if you look at the number of divorces occurring that year versus the number of marriages occurring in that year, for every 1 divorce, there's about 2 marriages. So that's where people try and claim that half of all marriages end in divorce, because every year, the number of divorces versus the number of marriages is about 1 to 2. For every 1 divorce, there's about 2 marriages. And look in 2010, about the same. 2004, about the same. 2000, about the same. 1990, about the same. 1980, about the same. But if you go further back, 1970 and on, it becomes less true. 700,000 versus 2 million, that's not the same as just doubling. 400,000 versus 1.5 million, that's definitely not true. So at some point around the 70s and 80s, this pattern changed. And they have you look at these in all sorts of different rates and just try and say, well, which one is kind of the best? How would you actually prefer divorce rates be explained so they're a little more accurate? And I wouldn't compare them to a total population because not everyone in the population is married. Not everyone in the population wants to get married, ultimately. Some people like just staying single or just having a domestic partner, if you will, whatever. Which rates seem to support the idea that half of all marriages end in divorce? Well, if you look at this one, at this column, divorces per 100 marriages, this is the thing where you're comparing these two values to each other as a ratio. And that's where you get that 50% approximation for the past roughly 50 years or so. Before then, that wasn't really the case. There were a lot fewer divorces per marriage. So does this conclusion that roughly half of all marriages end in divorce logically follow? Absolutely not. Absolutely not. It's just in a year, there's twice as many marriages as divorces. In order for that statement to be true, everyone would have to be getting divorced within a year. And I'm going to say this as jokingly as I possibly can, so please don't take offense to this, but it usually takes a while for you to grow disdain for your spouse to ultimately want to separate from them. You know, a couple of years. Yes, some marriages do end in a divorce within a month or weeks or a couple of months, but it's usually a few years before people start showing their true nature or just changing maybe too much for the other person, whatever it might be. We're not trying to get into the philosophical side of it too much. Then they show this scatter plot. Like I said, I'm just really quickly addressing this because it's one of my favorite activities, but it's long to talk about. So this is the divorces per 1,000 marriages total in the population. And this is ranking divorces per 1,000 marriages. So it's a ratio of divorces to marriages. And that's just total, not per year, total. And you can see that it's not too massive here, 5 divorces per 1,000 people that got married total. But over time, it's growing, it's growing, it's growing, it's growing. And if you look at the dots, we can see that there's a spike from 1960 to 1970 to 1980. And then all of a sudden, something changes dramatically and they start going down. Now this dot, that line of best fit is considering all of these points. But in this region right here, it's pretty good for the most part. I don't know about this one. That's a little further off than the rest. So this is okay, but in this region over here, it is completely terrible as a predictor because the line of best fit is going up, but these dots are showing a downward trend, in fact. The divorces are actually becoming fewer and fewer. So what's going on with this? What could explain the divorce rate starting to fall after 1980 and this model becoming garbage? Well, first of all, people started living longer. So looking at an annual basis becomes an even worse model. Second of all, the biggest and most important issue for us, not just for the model, but as a people in general, in the 1960s, we finally had what we call the No-Fault Divorce Act. So before some point in the 60s, I want to say later in the 60s, and California was the first state to enact this, I believe, you couldn't get a divorce from someone unless you proved that, I mean, you can probably imagine what was happening, why people were getting divorced. It was usually abuse. There were other reasons as well, but that was usually what happened. You had to go to court, show that there was abuse, and that's how you got out of a marriage. So if it was just, you don't like each other, tough cookies, you're staying married. So California passed this. Other states started passing it, I mean, almost instantaneously, and then it was done for our whole country in the mid-70s, I want to say. So that is why you see this explosion of divorces, because you had all these people in the 40s, 50s, and 60s that had gotten married, wanted a divorce, but legally were not allowed to divorce because there was no fault. It was just they didn't like each other. But then the floodgates opened up and the divorce rate just skyrocketed for a bit. And by skyrocketed, I mean it just like multiplied by about 5. But once you open the floodgates and you got all these people that had been married for 10, 20, 30, 40 years, they got their divorces that they wanted finally. Well, now they start dropping off again because everyone's allowed to get a divorce. So you can be 1 year in, divorce, 5 years in, divorce. So this was kind of a correcting factor, and now they've gone down some. Now, is this likely to continue to trend this steeply? I doubt it. I think that it is still going to continue downward, but not in as steep of a manner. And also the trend could completely change because in the past decade across the country, we've legalized marriage for everyone, not just opposite sex couples. So that could have an effect on the divorce rates. Would it have a drastic effect? I would say not too drastic because, just throwing a number out there, about 10% would be in this new classification, and 10% isn't exactly going to rock the boat as drastically, sorry for just making a bunch of noise, as this section right here. So this is a really wonderful example of how a mathematical model, when you look at it over too wide of a period, just falls apart because of some social dynamic. Also, we have a lot less people getting married now because it's a lot more socially acceptable to just live in a home together. In the 30s, 40s, 50s, your mom and dad were they're gonna beat you with a broomstick or something, right? I'm sorry for that joke. But nowadays it's, hey, I'm gonna do this. It's fine. Look at how many people do it. It's socially acceptable. All right. With that being said, I'm about to accidentally hit the wrong button. Let's get back to annotate, clear screen. I almost hit stop share, which thankfully there's a safety feature. We're done with chapter 5. And we have just enough time to start chapter 6. And let's not show too much at once. Constant percent change. And there is another name for this, and its other name is exponential growth or decay. Now, I'm going to remind you what your growth factor and decay factor are. Growth factor is 1 plus r, where a decay factor is 1 minus r. That was something we did back in chapter 4. And then we had some new amount is an old amount times a growth factor or decay factor. So you could have the minus if it's decay. That's what I'm saying there. But we're going to mainly focus on growth in this course. We don't do too much with decay. Very, very, very few problems with decay, in fact. Just our teeth. Ha ha ha. So we have seen that by using a growth or decay factor, when something is changing by a percentage over a year, that we can find the new year's amount based on the old year's amount times its growth factor, where the R is the growth rate. The growth or decay rate. Again, these are all just reminders. Everything I've said so far is not new. So this is like, all right, you have a savings account that gains 5% interest annually. So if you put $10,000 in the account, you can find the interest by just taking the 10,000 times your 5%, or you can find the new amount by taking 10,000 times 1 plus 0.05, which is the 5% converted to a rate. But all of that was only true for one small interval of time, typically a year, a month, or day, or whatever, depending on the problem. The problem has to tell you if you're growing at an annual rate or a periodic rate of a month or a day or a quarter or anything like that. And we will see both of these types of problems. So what happens if you want to find a new amount after several iterations? Let's say you put $10,000 in a bank account and you leave it there for 50 years, and you want to mathematically figure out, well, how much do I have at year 50? Well, everything that I've just said entirely relates to this new equals old times growth factor, but to find out how much you have at the end of year 50, you'd have to find what you have at year 49, and to find year 49, you got to do year 48. To do 47, you got to find 46. To do year 35, you got to do year 34. To do year 3, you got to do year 2. To do year 2, you got to do year 1. So if you want to find how much money you have in just using this simple concept, it would take you 50 rows of work. Now, if you're doing it by hand, extremely time consuming. If you let Excel do the work, all you got to do is set up your formulas, drag and drop, fill, boom, you're done. But at the same time, it's still going to take up a lot more space. So this is called an iterative method, where to do year 50, you got to do the previous 49 years. You can't just skip to year 50 using this iterative concept. I'm not saying there isn't a way to just go straight to year 50. There is. That's the ultimate point of this section and chapter. But what we need to do is actually develop a formula for it. So this is just to go from one year to another, or from 1 month to another, or from one day to another. So if I say your bank account is compounding interest monthly, that means if you wanted to find January of 2021, you'd have to go through year 2020, January, February, March, April, May, June, July, August, September, October, November, December. That would be 12 iterations. When you compound annually, it would only take you 1 iteration. If we compounded daily, oh boy, buckle up, because you would have to do that problem 365 times just to get to the next year. And that's where you would go, oh, I'm going to use Excel. You better believe it. All right. So again, iterative method, new equals old times growth factor. Is everything with a percent of growth factor? No. You have to understand the concept. And some of you did pretty good with that idea on the previous test. Some of you were trying to do one type of percent problem and another type of percent problem. So got to get your ducks in a row. So here's what we're going to do. We are going to develop a formula that we will be able to use for compounding rates. This is when you will get growth off of the old and previous growth. So the idea of compound interest has been addressed in here very lightly previously. We saw when we had that TV loan problem, when we weren't paying it off at all, the interest for the first month was, say, $10, just throwing a random number out there. But then the interest for the second month was like $10.10. And then the interest from the third month was like $10.21. And then $10.32. That interest amount kept going up because when you take that interest and you add it onto the balance, your balance is bigger. Your interest is a product of the balance. So if your balance goes up, your interest goes up. And it causes this idea of compounding. You're getting money on money. It's when you get growth off of the old and the interest. Interest being previous growth. So we're going to develop a formula to be able to go straight from year 0 to year 50 or to year 1000 or to year 2, whatever we want, without doing all the middlemen and women. So I'm giving a big hint for this. After each time interval, the new old will be the previous new. This idea we've already addressed in Excel. I circled one less word than I meant to. The new old will be the old new. And in other words, when you find your balance at the end of year 1, say it's $10,200. That's your starting balance for year 2. And then, sorry, I got something in my throat. Whew. Oh, that was bad. I'm glad I muted for that one. Okay. Where was I? I've lost my train of thought. The new old is the old new. So your beginning balance of year 2 becomes an ending balance of year 2 after you get your interest. Then that ending balance of year 2 becomes the beginning balance of year 3. Then you gain interest, and that becomes the ending balance of year 3. And then that value becomes the starting balance of year 4. So the new old will be the old new, and we're going to end up chaining some things together to condense this formula if we're doing it right. So let's talk about, and these are just some letters we're going to see later. Give ourselves some good space. Let's go to year 0. Year 0, before we gain any money, we've just got some old amount. I'm using generic words. And if you wanted to give that a letter like P later, we will. So that's the old amount. That's the original amount. It's just another way of saying original. That's our $10,000 deposit that I keep talking about. So you can call it old or original. Then in year 1, I am so sorry, everyone. All right, year 1, well, at the end of it, at the end of year 1, so that's what I'm talking about for each of these, we'll have a new amount. And that new amount is the old amount times the growth factor, which is the old amount times 1 plus R. Our growth factor, we're growing money. We're usually growing in this course. It is rare that we're decaying. We will see a couple problems. If it was decaying, it would be 1 minus R. That's the only difference. Our money is growing. So this is the new amount. It's the old times 1 plus R, or the original times 1 plus R. Okay, so let's just hold on to that, and now let's go year 2. The new amount in year 2, now this is not the same. These are not the same. I'm talking about the new amount in year 2. The new amount in year 2 is not the new amount in year 1. So this is the previous amount. I'm not trying to say old or original here. I'm trying to say the previous amount from the previous year. It's not necessarily the original value. And in fact, when I say old, I do want to erase that and call it original. It's a little more sensible that way. Because if I say old, you might be thinking in year 5, I'm talking about the old of year 4. Okay, so the new amount should be the previous amount times the growth factor, which is 1 plus R. But here's the thing. The previous, oh, why is it so bad today? The previous amount, this is like us linking that Excel. It's the ending amount from year 1. In year 2, the previous amount means the ending amount from year. So those two things are the same. So I'm supposed to write, and I'm going to write it in blue to show you the change. It's the original amount times 1 plus R. Again, this right here was this right here, which is this right here. But that's not the whole thing. There was also this 1 plus R next to it. So again, in blue, this was the highlighted section. The previous amount, which was the original amount times the growth factor. So now in year 2, we still have that original amount in the problem. That's kind of cool. It's still going to harken back to our 10,000, but look at this. There's an extra 1 plus R. There's 2 of these bad boys. So if you have 5 times 5, that's 5 squared. If you have x times x, that's x squared. So we could compress this. You will need to chain some things together. Compress, chain, that's what I'm talking about. As the original times 1 plus r to the second power. 5 times 5 is 5 squared. X times x is x squared. So 1 plus r times 1 plus r is 1 plus r squared. So that says that the new amount in year 2 can be calculated as whatever you have as your original amount times the growth factor squared. Now let's go to year 3. The new amount for year 3 should be the previous ending amount times another growth factor. Now when I say previous amount, That's the ending value from the previous year. So look at this. This original times 1 plus r squared, I'll write that in red since I have it red underlined. So the previous amount here, I'm going to write what I have here. Instead of writing previous, I write original times 1 plus r squared. So original times 1 plus r squared. But we still have this extra 1 plus r that needs to go here. Are you starting to see the pattern? So 1 plus r squared times 1 plus r, you can condense that, you can compress it, you can chain it together. It's just the original times 1 plus r to the, all right, what's 5 squared times 5? It's 5 cubed. What's x squared times x? It's x cubed. That's 1 plus r cubed. And you could do this year 4, year 5, year 6, year 7, however long you need to do this. We'll do it one more just to make sure we've got this hammered in. The new amount for year 4 should be the previous amount times an extra 1 plus r. We get an extra 1 plus r each year. We get an extra growth factor each year. But this previous amount should be the ending amount from year 3. So in blue, I'll write original times 1 plus r to the third. But we have the extra growth factor, giving us the original times 1 plus r to the fourth. So year 5 ends up being original times 1 plus r to the fifth. Year 6 ends up being original times 1 plus r to the sixth. Year 20 ends up being original times 1 plus r to the 20. Let's generalize this and say year t. See, we kind of did a process like this on that test, if you remember. The new, and let's just go straight to this. All right, so for year 4, the exponent was a 4. For year 2, the exponent was a 2. For year 1, the exponent's a 1. So if we have year t, this should just be the original amount times 1 plus r to the t. And there it is. So this just says any new amount can be found to be the product of the original amount times the growth factor raised to however long you're looking into it. So if you're looking 50 years in, then your exponent's a 50. That looks like a terrible exponent. Let me make that a little prettier. There we go. This is the concept of exponential growth. Its picture is not a line, it bends. And I will show you what that bending looks like in just a minute. So this, what this will do for us is allow us to find for any year t without the iterative process. So if you want to know year 50, you go straight to year 50. If you want to know year 2000, you go straight to year 2000. If you want to know year 5, you don't need years 1, 2, 3, and 4 to find out year 5. Now, both concepts are equally important. We definitely need the iterative version of things because a lot of people want tables of information and to see how everything has changed over time. But then there's a lot of people that just want to know what's the ending value, what am I going to have at the end? And they don't need the middleman. So lines, we know what a line looks like. A linear model looks something like this. It doesn't have to necessarily start at that height. It can start at the origin, it can start below it, but that's a linear model. An exponential growth model ends up looking something like this. It usually has some starting value. It could, you might think it can start at 0, but it actually can't unless it has a shifting factor, which we won't be applying in this course. So it has some starting value still. But what happens is, it starts out pretty slow at first, and then at some point, roughly around here, it starts growing faster and faster until at some point way up here, it eventually explodes. So in the fast zone, I like to say that it explodes. Exponential explosion, you can see why I like that word. because this thing just picks up pace insanely fast. Now, at what point of time, how many years in, that's highly variable depending on your growth rate, your compounding intervals, your starting value. It's definitely going to depend on the context of the problem. Sometimes we can see this explosion of money in maybe 10 years with a high growth rate. Sometimes we might see the explosion happen in like 40 years because we've got a very slow rate, or maybe 100 years because it's a ridiculously low rate, like a savings account at a brick and mortar bank, earning 0.1% interest. Ugh, terrible. All right, so this idea of NEV, I said erase, please erase, thank you. The new amount is the old times the growth factor raised to an exponent that's your time. So what we're going to do is we're going to take that thing, which was new equals original times 1 plus r to the t, and we're just going to give it less, what? There we go. We're going to give it some more common letters, and please note these are not the only letters you'll see in this course. So A, the future value, that's what we call the new. P, the principal, that's what we call the original. R, the annual interest rate, there's no surprise there. T, the time in years, there's no surprise there. So when we compound annually, when we gain money once per year, or whatever it is we're gaining, it's not always just money. Maybe we're talking about gaining cells over a year or something like that, which is not a great model, but you certainly could make it. All right, so compounding annually, A, which is the future value, that's the new, equals P, the principal, which we said is the original, times 1 plus r, that's your growth factor, and then raised to the amount of time in years. And please note that this is for compounding annually only. I would prefer that you memorize this formula. Whether or not I'm going to put it on a formula sheet, which I'm not saying yet. For now, I'm going to say you need to memorize this formula. Maybe I don't make you memorize it, maybe I do. So here's the thing. For these next several chapters and sections, we're going to be giving you a bunch of formulas, and they kind of start from here and they just get worse and worse and worse. Now, the worse and worse and worse ones, I will give those to you on a formula sheet. I will put it in Canvas very soon, over the next couple of days, if not the next week. And all I'm saying is maybe I put the compounding annually up there, maybe I don't. And I'll even admit, I change this from semester to semester. Some semesters I make my students memorize this one, some I don't. And I have a reason for that, and it's because this is the base level of exponential growth, so I feel like it should be memorized. However, you can also figure this out based on some of the formulas of the formula sheet if you just kind of trim the fat on one or two of them. And I'll even tell you how to do that, in fact. All right, so that's for compounding annually only. I'm going to give you a hint as to what we'll be talking about some next time. What if we were to compound on a shorter interval, like months or quarters or days? What change happens to this formula? Because two of these things are going to change. Maybe it's the P, maybe it's the R, maybe it's the T. Two of those three things will change. We'll go through that process next time. I'm thinking, I already have a quiz and an Excel due on the 19th, so I'll save the discussion board. But just an FYI, there will be a highlighter, a discussion board for page 224 assigned next class that would be due on the following Monday. So, does everything in the world grow exponentially? No. When you get money at your job, is your salary growing exponentially from paycheck to paycheck? No. If you get an annual pay raise, is your annual salary increasing exponentially? Actually, yes, if your pay raise is exactly the same every year. It's pretty rare that that happens. If you're a state employee, your pay raises pretty much never happen. Two thumbs pointing in my direction, as I always like to point out. But there are tons of things that grow exponentially. Your money, if you're not adding to the pile of money in a bank account somewhere, if your interest rate never changes, it's growing exponentially. If we had a virus spreading through our community at a constant rate, then it would spread exponentially. Now, if you only look at a small interval of time, that virus is spreading at an exponential rate. But when you look at larger values of time, that rate changes due to maybe social distancing changing, as well as the fact that there's a cap on the population. So we can't just say eventually 10 trillion people are going to get infected, because there aren't 10 trillion people to affect. It would have to slow down at some point. But a virus spreading and gaining money in a bank account are two completely different things in the long term. So let's go ahead and call it there. We will probably pick up right at the discussion of page 224's discussion board next class, which very much relates to everything we just did in this iterative process. Actually, I say 224, I might use 226. I might do one, I might do both. Maybe I'll do one in class and have you do the other. I'm going to think about that. I've done a mixture of things. As I've said, I kind of teach little bits and pieces of this class different each semester. Sometimes I make things discussion boards. Sometimes I talk about them myself instead. It just depends. We have so many different ways we can do things. And that's the theme of the class.
So we'll call it there. And obviously, when I said discussion board due on a Monday, that was wrong. We've been doing Tuesdays and Thursdays for all of our due dates. So again, clearly just these little subtle changes from when I made the primary recordings. So 5.1, 5.2, 5.3, 5.4, all of chapter 5, homework assignments on the horizon, November 9th, November 11th, November 16th, as we've discussed already. Excel 5.1 lines, do this Thursday the 11th, as well as the second video quiz, do the 11th. Remember that you'll need to handwrite or type your answers and then upload that where it says to submit it here in Canvas. And remember that the next several quizzes after this will all be video quizzes. There will be a video quiz 3 for chapter 5, video quiz 4 will be on chapter 6 and 7, and then video quiz 5 will be on chapter 9. And that is likely to be all of our quizzes for the semester, except for maybe one more, depending on how things go. We'll see. But for now, as always, have a good day, work hard, start studying this stuff, keep all the material from chapter 1 through 4 fresh in your mind, because the final exam is not that far off, just a month and some change. And remember, the final is cumulative. And then as well as don't forget your project that you're working on all along the month of November. But if you have any questions, shoot me an email. Besides that, we'll see you next time. Take care, everybody.